Okay, now let's continue the discussion in thermodynamics. So I already uploaded the first video, and for the second part, we'll be discussing more about, um, I guess, uh, thermodynamic processes and laws of thermodynamics. Okay, so for the first part, the process is any change that a system undergoes from one equilibrium state to another. Okay. And a path refers to the series of states through which a system passes during a process. So when you go from one state to another, um, the path is your your change of states, okay, during the process. A reversible process is one that is performed in such a way that at the end of the process, both the system and the local surrounding can be restored to their initial states. That's your reversible. Well, basically, it's self-explanatory. If you can reverse the process or you can return it back to its original state, that's your reversible process. If a process does not meet these requirements, it's said to be irreversible. Okay. There are others also that's a reversible process where you can't return to the original state because something really happened along the way. Okay. So what are these thermodynamic processes? Let's start with isobaric. These terms are mm, mostly asked in the board exam. So you need to consider what are the meaning of these processes. But basically, there are hints within terms used. Like, for example, isobaric process is a process in which the state variable of the system is changed while the pressure is held constant. So there's the keyword there. When you make the pressure constant, it's a isobaric process. So there's the keyword bar that used to consider pressure to be constant. If it's an isovolumic, so basically, I guess the keyword here is that it's the volume that is held constant. So also known as the isometric or isochoric process, is a process carried out at constant volume. Okay, so there's your keyword there, your isovolumic. Next is adiabatic process. Well, adiabatic is basically has two different types. I mean, it's an isentropic and a throttling or isenthalpic. Okay. But what's adiabatic process? One in which there's no heat or other energy transferred to or from the system. Okay. It's like your isolated system earlier, but um, you need to consider for adiabatic process, we have two types, the constant entropy or the constant enthalpy. For the constant entropy, it will be easy because the keyword here is isentropic, entropy. So um, it's an adiabatic process where there's no change in system entropy. Okay, later we'll discuss about entropy. Now, what is enthalpy? It's an adiabatic process where there's no change in enthalpy, but for which there's a significant pressure drop. That's why it's called, well, it's also called isenthalpic process, but also known as the throttling process. Well, if you want to differentiate about entropy and enthalpy are the useful energy and entropy are not useful energy. They're like noise in the system. Okay. So isothermal is uh there's your keyword here, thermal or thermal. It means temperature. So when the pressure is constant for this process, we have isothermal process. So we basically have five types for now. You have the isobaric, isentropic, isovolumic, isothermal, and we have the isenthalpic or the throttling process. For a polytropic process, you have the product of pressure times volume raised to the power of n is constant, and we have different values for n, which corresponds to different types of process. Okay. So for a polytropic process, you have these formula PV raised to n equals is constant. Well, depending on the value of n will corresponds to a different process also. Okay. But the keyword here is, well, actually my mnemonics here is the formula PV raised to n. Okay. Like for example, when you make the n be equal to zero, so your V raised to zero now will be one. And it means that pressure is constant. When your pressure is constant, that's an isobaric process. There you go, isobaric process. And if n is one, well, you basically have PV raised to 1, or the product of pressure times volume is mostly equivalent to temperature. Like, for example, you go back to gas law, PV is equal to nRT, or you can say that the product of pressure times volume is also numerically equal to temperature. So when that temperature is constant, you have your isothermal process. Okay. Then let's go first to n is infinity. When n is infinity, your pressure really doesn't matter at all. So it's only about volume. So when the volume is constant, because n is infinity, if volume is constant, you have your isovolumic or the isometric or isochoric process. And for the different types of n, you have 0, 1, and infinity. Any other value, such as 1.5 or 2.3, or any value wherein n is k, okay? So when you have a different value other than 0, 1, and infinity, you have your isentropic process, okay? So this is, I guess, once asked in the board exam, so you need to consider the polytropic process. Okay. For heat, there's a computation here that you need to consider. It's a transferred energy that arises from the random motion of molecules. We have different types of transmission of heat. We have the first one, the conduction, in which heat transfers from molecule to molecule, or you need to touch, or molecules will need to touch through bodies in contact. So that's your conduction. Okay. Other types of transmission of heat is convection. Convection is there's no real contact, but there's a medium that used to transfer the energy. Okay, that's convection. And when there's no medium involved and there's no contact, you basically have your radiation as the transmission of heat, which the heat transfers without any intervening medium, without contact. That's your radiation. One good example of radiation is the radiation from the sun. That's how the sun transmit the energy through radiation. Convection is somehow, well, when you have a process and you have a conduit or a pipe or something that used to be considered as medium, that's your convection. And basically, when you have conduction, that's really in contact, transfer in contact. Okay. Now, latent heat. So it's the amount of heat necessary to change the phase of the system without changing it at its temperature. So, for example, you have an ice and the ice changes from water or from ice to water. You basically consider there's a transfer of heat there, and you call this with the amount of heat that was transferred through the ice to make it water is called your latent heat. Specifically, that's a latent heat of fusion. Okay. So fusion is for ice to water, or you can consider also water to ice, because sometimes your value for the heat is plus or minus. So when it is a plus or it's a positive, the heat is absorbed by the substance or the substance melts. If the heat, on the other hand, is minus, so it actually releases the heat, or the heat was removed from the substance, it now freezes, right? So that's your definition of plus or minus. But we can consider also the next one, which is the heat of vaporization, wherein it's the changing of phase from water to gas. Okay, so water to gas. When it absorbs heat and it's a positive heat, it's now changing from water to air molecules. But there's also a process wherein you reduce the heat from that air molecules. That's your um, negative heat of vaporization. That's now changing from water or from air molecules to water. Remember that we have that process in chemistry. We call it condensation, maybe, if you still recall. It's from air to liquid. Okay, later we will be computing these values, but let's start with the latent heat of fusion, or the latent heat of fusion is the heat necessary to change a unit of mass of substance from solid to liquid, or liquid to solid, or vice versa, without changing the temperature. So when we don't have a change in temperature, we have the latent heat. Okay. The formula earlier is mass times H, where H is the heat of fusion or vaporization. So we have the constant value for fusion. You only have 80 calories per gram. So the amount of grams, for example, ice, they have 100 grams. So in order to melt the ice of 100 grams to water, you need 80 calorie divided per gram multiplied by 100 grams. You need to have at least 8,000 calories to change the 100 grams of ice into water. These are the other units of heat of fusion, the 144 British thermal unit per pound, or 334 kilojoules per kilogram. But we usually use the calories per gram, so don't worry. We can convert also calories to kilogram also, and grams to kilograms. Or you can also convert kilojoules to BTU later. Okay, I'll show you how to do it. For the latent heat of vaporization, is the heat required to change a unit of substance from liquid to the vapor state. Okay. And it has a lot of energy needed. So that's why you need to consider it has a high value of 540 calories per gram. So for example, you have 10 grams of water, you need to convert it to um, water vapor. You need around 5,400 calories. So these are done using kettle, or mostly kettle, to convert water into into vapor state. The conversion again, you can memorize 970 BTU per pound, or you can just convert it later, or 2257 kilojoules per kilogram. But you need to consider memorizing at least one from these heat of vaporization and fusion. So recall that for heat of fusion, you have 80 calories per gram, and for heat of vaporization, you need at least 540 calories per gram. Okay. So these latent heat are the change of state, right? The amount of heat absorbed or released without changing the temperature. If we change now the temperature, we need to consider the sensible heat. It's the amount of heat necessary to change the temperature of the system without changing its phase. So the formula is M, or the mass. C is the specific heat, wherein it's the amount of heat required to raise the temperature of 1 gram of the substance by 1 degree Celsius. So mostly specific heat are given, but the unit of specific heat are calories, or sometimes it's joules per degree Celsius. Okay. And then you have there your change in temperature to complete the formula. And remember, you're using sensible heat when there's heat absorbed or release, and there's always a change in temperature. Okay. If there's no change in temperature, we don't consider the sensible heat. So now, total heat. Total heat is the amount, or the sum of the latent heat and the sensible heat. Like for example, you want to change water, or you want to change ice into its weight in its water vapor. You cannot directly go from ice to water vapor. You need to change the state first by considering the latent heat of fusion from ice to water, and then you change the temperature of water. That's your sensible heat. So from um, water, which is 0 degrees Celsius, to 100 degrees Celsius. Now, if you want to change it to water vapor, you just consider the heat of vaporization there. That's your total heat now. Okay. Later, we'll have an example for that. And then we have the entropy. Entropy has the formula, or this is actually a measure of energy that is no longer available to perform useful work within the current environment. Other definition is that it's the measure of randomness or disorder of the system. If you can recall, I mentioned about entropy being the noise because it's a measure of randomness or disorder of energy in the system. The formula for the entropy is heat per temperature. So basically, you can use heat in terms of joules or calories. So the entropy has a unit of joules or calorie per Kelvin. You need to consider that temperature must be in Kelvin because, as I've said earlier, if you use in degrees Celsius and you're using 0 degrees Celsius, you'll be considering entropy become infinity, and we don't like that. We own we don't like the noise to become a very large value. Okay. Next, another formula for entropy for constant pressure for isobaric process is MCP, natural logarithm of temperature 2 over temperature 1. CP is the specific heat held at constant pressure. Okay. The unit for the change in entropy there is still joules per Kelvin or calories per Kelvin. But you need to consider memorizing this formula. Although there's not yet a question in the board exam that was asked about the entropy in isobaric process. Maybe it's in your board exam. Hopefully not, but we just want to be prepared. Okay. Another formula is for specific heat held at constant volume. So that is your MCV ln, or natural logarithm of T2 over T1. Okay. So since it was held at constant volume, this is the entropy for isometric process. And for isothermal process, you need to consider the ideal gas constant. Okay. We don't have a specific heat for that. So, but you're taking the natural logarithm now of volume 2 over volume 1. Okay. That's what you need to change for the entropy change in isothermal process. And then for an adiabatic process, since we have mentioned that one of the types of adiabatic process is isentropic process, wherein there's no change in entropy. Since there's no change in entropy, your delta S is equal to 0. Okay? Then we go to the useful energy, which is your enthalpy. So internal energy is of the system is the total energy content of the system. It's the sum of the kinetic, potential, chemical, electrical, nuclear, and all other forms of energy possessed by the atoms and molecules of the system. Okay? It can be useful or not, but it's still basically your total energy in the system. That's your internal energy. How about enthalpy? It represents the total useful energy of the substance. The useful energy consists of two parts. The first one is the internal energy. Okay, so for this time, the internal energy is always the useful energy. And the flow energy, also known as the flow work, it has the formula of product of pressure times the volume. Okay, so you need to memorize this one. The enthalpy is internal energy plus flow work. And let's answer different problems for now. It indicates that the rate of heat conduction in the direction is proportional to the temperature gradient in that direction. Rate of heat of conduction, there's the word conduction here. So I'll basically choose the Fourier's law of heat conduction because you can't usually consider radiation when there's a conduction happening or convection when there's a conduction happening. So I think I'll consider letter A. Yeah, there you go. Letter A is the correct answer. Next, a 20-gram piece of aluminum with a specific heat of 0.21 calories per gram at 90 degrees is dropped in the cavity into a large block of ice at 0 degrees Celsius. How much ice does the aluminum melt? Wow. Okay. Let's solve this problem. It's kind of difficult problem, but I think we can still solve this one. Let's consider a large block of ice. Okay. So for example, this one. And then there's an aluminum here. It's around 20 grams. Okay. So 20 grams of aluminum. Okay. Aluminum. Now, the temperature of that aluminum is 90 degrees Celsius. So when it touches the ice, there will be water that will be or no, there will be ice that will be transformed into water. So for example, this is your water now. Okay. So the question here is how much ice does the aluminum melt? So since it's a 90 degrees Celsius, that aluminum will give heat to the aluminum or to the ice, and that part of ice will melt, and that's what we want to solve. Okay, around how many grams? So at first, there's a change in temperature for the aluminum. We'll need to compute for the sensible heat of the aluminum, which we will use MC delta T. Okay, the mass of the aluminum is 20 grams. The specific heat of aluminum is already given, 0.21 calories per gram degrees Celsius. 0.21 calories per gram degrees Celsius. And the change in temperature is 0 to, where that's your final. Initial is 90. So it's now negative because the aluminum gives off heat, and that heat will be absorbed by the ice. Later, that negative will change to positive when you consider ice that will melt because of that heat transfer. So this is now equal to what? 20 times 0.21 times 0 minus 90. Okay, 300 negative 378 calories. The gram will cancel, degree Celsius will cancel. By the way, you have this one as degree Celsius. So um, that's it for the sensible heat. Now, that heat will be transferred to this block of ice, and there will be part of that ice that will melt because it will absorb the heat of the aluminum. And that basically is your latent heat. Okay. And it has the formula MHF. So this mass now is the one that we want to solve, and this latent heat is actually the same with the sensible heat, but with a positive value because it absorbs now the heat energy coming from the aluminum. So this is 378 calories and then equal to the mass multiplied by the heat of fusion, which is, or sorry, the unit is 80 calories per gram. So when you cancel this 80 on our left side, calories will cancel and you have your unit of mass be equal to grams. So I just need to simply divide 378 by 80. And there you go. This should be your answer. 4.725 grams. So at first it looks like a difficult problem. Well, it is, but as you understand how we understand the types of process or the heat transfer, you can easily solve this one. Okay. Next, water is being heated by a 1500 watts heater. What is the rate of change in temperature of a kilogram of water? Okay. Now, we don't really discuss yet about power, which is in watts unit. So let me just consider that when we say we have the power equal to 1500 watts, this is the same as saying this is 1500 joules per second. Okay. So that's actually your unit of power or watts. It's the amount of energy per unit time. So we can also say this is also the amount of heat with respect to time. That's why it's called the rate of change. So when you say rate of change in temperature of a kilogram, so the question here is rate of change in temperature with respect to time. So your sensible heat now is it has a change in temperature with respect to time. That's the rate. You just place MC or mass times specific heat here. So we're still consistent with our sensible heat. MC delta T, we just divide that with time. Okay. So, well, the question here is the change in temperature with respect to time. So we need to consider sensible heat over time over mass times specific heat. Okay. But what's your sensible heat with respect to time? That's actually your oops. That's actually your power. Okay, the given power. So the 1500 watts is 1500 joules per second. The mass is a kilogram. Okay. I'm gonna use 1000 grams. Why do I use 1000 grams? Because I know that the specific heat of water is 1 calorie per gram degree Celsius. Okay. As for this matter, because this is now change in temperature, so I can also say that these degrees Celsius or the change in temperature in degrees Celsius can also be converted into degrees Kelvin. Okay, if you know what I mean. I just discussed that earlier. But the problem here, another problem is that the unit of power is joules, and this is in terms of calories. So there are two choice that we can use. First one is convert joules into calories or calories to joules. Okay. I have my calculator to tell you that we have also a conversion for our calculator that used to convert calories to joules. Let me think about number. I think it's convert 40. Okay, there you go. So your 1 calorie convert 40, sorry, convert 40, 0. Okay, that's calories to joules. You have here how much? Around 4.1858. In other contexts or in other books, they use 4.2. So I'm well, it's your choice. I'm just gonna use a 4.2 joules, 4.2 joules in 1 calorie. Okay, calorie will cancel. The joules will cancel now. Your grams will cancel. So our unit will be Kelvin with respect to time. Okay, so let's try that. It's 1,500 divided by 1,000 grams times 4.2 joules. 5/14 or 0.357, which we have the unit of Kelvin. 0.357 change in temperature Kelvin with respect to time, seconds. Okay, so let's check our answer. Oh, it's around, let's see. That's it. Next, we go to this problem. 1 kilogram of water, specific heat is given, is heated by a 300 BTU of energy. What is the change in temperature in Kelvin? Now, this is already in change in temperature, but the problem here is that the energy given is in BTU. So I told you earlier that I'm going to show you how to convert British thermal unit to joules or calories. So formula is sensible heat, mc delta T, but the question here is the change in temperature. So change in temperature is the sensible heat over mass times the specific heat. Specific heat is already given as 4.2 kilojoules per kilogram degree Kelvin, so I don't want to consider the 1 calorie per gram. But the sensible heat is your 300 BTU of energy. So we need to convert that to the unit of our specific heat. And by the way, what's the mass? 1 kilogram. So I'm going to write first the mass, 1 kilo. The specific heat is 4.2 kilojoules per kilogram degree Celsius. Okay. And the unit of um, our sensible heat is 300 BTU. So we want to convert to kilojoules so that we can cancel from the specific heat. Now, the conversion factor is actually, if I can remember it right, it's 1 British thermal unit is around 1.055 kilojoules. Okay, you can check. You have your internet to verify it, but it's something that I still remember when I was reviewing. So let's try this one. This is 300 times 1.055 to make it in kilogram or kilojoules. Then 1 kilogram times 4.2 kilojoules per kilogram. So as you can see, kilogram here will cancel. The British thermal unit will cancel. The kilojoules will cancel. You only have now the change in temperature in terms of degrees Celsius. Well, I can also consider that in terms of Kelvin, if you know what I mean. So this is around 75.375. 357 M. Okay, degrees Celsius. Or as I've said, you can also consider it's in Kelvin. So this is because of change in temperature in Kelvin is the same but in terms of Celsius. So we'll be considering around 75.4 Kelvin. Okay? Okay. That's it. The next problem is okay. So this is an English system wherein find the change in internal energy of 5 pounds of oxygen gas where the temperature changes from 100 degrees Fahrenheit to 120 degrees Fahrenheit. Specific heat at constant volume is 0.157 BTU per pound mass. We don't need to convert BTU into joules because we already have our choices in terms of BTU. So we only need to execute this problem using the formula sensible heat is MC delta T. Okay. Your mass is 5 pound mass. Your specific heat is 0.157 BTU per pound mass degree Rankine. And then the change in temperature is 120 final minus initial 100. But this time, even if it's in terms of Fahrenheit, I can just use in terms of Rankine because this is in we're considering change in temperature here. So Rankine will cancel, pound mass will cancel. We only have the value in terms of BTU. So sensible heat now is basically equal to 5 times 0.157 times 20. Where did I get 20? That's your 120 minus 100. And the answer is 15.7 BTU. I really hope it's in our choices. There you go, letter C, 15.7 BT. And as I mentioned, you don't need to convert. Just look at the choices. Next is the compute the entropy change of, okay, so the entropy change here is joules per Kelvin. Uh-huh. 5 gram of water at 100 as it changes to steam at 100 under standard pressure. Okay. So our change in entropy S is equal to M or Q over T. Okay. Your Q is actually, we didn't change the temperature, so we will be using HV. Why did I consider HV? Because of the changing of 5 grams of water to steam. So it's the latent heat of vaporization divided by the temperature in Kelvin. So again, this will be easy. The mass is 5 grams. We just need to execute it. And then, by the way, it's in joules. So instead of using um, 540 calories, we will be using how much is that? 2247 joules, I guess, per joules per gram. Well, I can still use the 540 calories if I forget about in terms of joules. I just need to convert calories, which is 1 calorie is 4.2 joules. Sorry. Okay. Divided by the temperature, it should be in absolute, so that's 100 plus 273 degree Kelvin. Okay, so change in temperature or change in entropy is now equal to, using our calculator, that's 5 times 4.2, but this one is 540, 540. Well, we still have the denominator to be 373. And there you go. It should be your answer around 30.4. Joules per Kelvin. How come it's in joules? Calorie will cancel out, grams will cancel, and you have joules per Kelvin. Let's check. Oops. It's 30.4, but the closest answer that we have is around. Well, the reason why it's 30.4 from our choices or from our answer because we just use 4.2. If we will be using the exact value of calories to joules or vice versa, which is 4.186, I think we should be getting around 30.3. Okay. And another review question is in extraterrestrial space, heat is transferred by what? Obviously, it should be radiation because we don't want any extraterrestrial body that will transfer heat to Earth. Okay. So we go now to our last topic, which is the laws of thermodynamics. We need to memorize most of these because we have four laws. Well, we started with zero law. So the last one will be third law. So the zeroth law, I have a keyword here. It's about thermal equilibrium. Okay. So the keyword for zeroth law is thermal equilibrium. I don't want to um, read it out loud. Okay. Next, first law of thermodynamics is it's about conservation of energy. Okay. So it's the amount of heat flows into a system. If an amount of heat flows into a system, then this energy must appear as an increased internal energy for the system and or work done by the system on its surrounding. The easiest keyword for first law is the conservation of energy. In other books, they consider it as energy can neither be destroyed nor created. It can only be transformed from one form to another. Okay? That's your first law of thermodynamics. And we have this formula, the total energy entering is equal to the total energy leaving. The sensible heat is now change in internal energy plus work done. For isobaric process, we still have this formula. Now the change of or the work done now was changed to product of pressure times the change in volume. Okay. For isovolumic process, we don't have the work done because we don't have the change in volume because it's a constant volume, isovolumic. So now the heat is equal to the internal energy. For isothermal, on the other hand, we don't have the internal energy. So we will be considering only the work done. Okay. Which has the formula also of P1V1 multiplied by the natural logarithm of volume 2 over volume 1. But this is seldom used. Okay. Honestly, I don't really memorize this one. For an adiabatic process, there's no heat. I mean, there's no sensible heat. Okay. So delta Q is 0. Now, it's equal to change or internal energy plus the work done. Or basically, transposing the work done, it's the negative of the internal energy. For the second law, the heat energy flows spontaneously from hotter to a colder object, but not vice versa. Okay, I remember considering second law as the keyword here is from hotter to colder and not vice versa. So they um, just remember this one. Whenever someone tell you about turning off the air or I mean close the door because the aircon or the cool air from aircon is going outside, or like for example, the cool air from the refrigerator is, I mean, it's not efficient because it's um, going outside from the refrigerator or using the aircon. It's not actually the case. the cool air from the aircon or from the refrigerator is not actually going out. It's actually the heat. Heat is going through the refrigerator or going through inside the room where the air condition is turned on. So that's how you consider the second law. Remember your air conditioned or your refrigerator. The other terms, now, no heat engine that cycle continuously can change all its input energy to useful work. You memorize this one. Um, I usually want to consider the first definition and the third definition. If a system undergoes spontaneous change, it will change in such a way that its entropy will increase or at best remains constant. We want to make the entropy remains constant because we don't want more unuseful work to be added in the system. So that's how second law of thermodynamics is. We don't want the heat coming from the refrigerator because that will make our refrigerator be inefficient and it will cost you a lot of money when the bill of electricity will go out. Okay? And the last law is the third law. The keyword here is since from the second law, we want to make the entropy be remain constant. But this time we want the entropy become zero. We want it to be efficient. There's no entropy, but this is ideal situation. Okay. I remember there's an engine and the most efficient engine which was not developed. It was really a theoretical engine. It's called Carnot engine. Before he finished his work, he died. So we weren't able to experience the most efficient engine. But that was a question in the board exam. It was asked around, I think, 2012. What is the most efficient engine? The answer is simply Carnot engine. The Carnot spells something like this. Carnot. Carnot. Okay. This is the most efficient engine, but it was an ideal engine. Okay. And there you go. This will be the last problems that we were going to solve, and we're done in thermodynamics. If a system absorbs 500 calories of heat at the same time, does 400 joules of work, find the change in internal energy of the system. So, as you well know, the the formula for the change in heat is change in internal energy plus the work done. Okay? But the question here is the internal energy. So, change in internal energy now is change in heat minus the work done. Okay. So what's the heat? Um, it absorbs 500 calories of heat. 500 calories. And we will subtract 400 joules of work. So don't just consider 500 subtracting 400 from 500. I mean, 500 minus 400 is 100. But we actually have two different units. So we want to convert our calories in terms of joules because our unit of choice is in joules, and the 400 joules must be converted into kilojoules. So how do we do that? Um, as you all know, we have the conversion of 1 calorie is 4.2 joules. Then we just subtract 400 joules. By the way, we don't need to convert yet the 400 joules. So we just need to convert or compute this one as it is for now. So 500 times 4.2 minus 400 joules. Okay, we have 1,700 joules, or that's basically 1.7 kilojoules by dividing it to 1,000. Okay, so that's it. I guess that our answer is letter C. Next, steam of 1,000 pounds foot square pressure and 300 Rankine has specific volume of 6.5 foot feet cube per pound mass and a specific enthalpy of 9,800 pound force foot per pound mass. Find the internal energy per pound mass of the steam. Oof. Okay. Hmm. We'll be using the formula. Enthalpy is your energy. That's your delta Q, which is internal energy again, plus the work done. But the work done will be using pressure times the volume. Okay, so this is a pressure of 1,000 and the volume is 6.5. Why do we use specific volume? Because all of the units are in terms of pound mass, eh, even if it's energy, it's in pound mass. This is also in pound mass. So the volume here is in pound mass as well. Okay. Now the question is internal energy per pound mass. So this will be your heat per pound mass plus the pressure times specific volume, or it should be minus, sorry. So minus pressure times volume per pound mass. As simple as it is. Now, another problem is, okay. Hmm. The enthalpy is 9,800 pound foot, pound force foot per pound mass. So 9,800 pound force feet per pound mass. We don't need to convert because our choices are in terms of that unit. Okay. Next, the pressure is around 1,000. We must be consistent unit here. So pound force per feet square. That's your unit of pressure in terms of area. Then specific volume is 6.5. So specific volume is 6.5. Unit of this one is feet cube per pound mass. So as you can see, the feet cube will cancel out with the feet square. And there you have your foot or pound force foot, okay, which is consistent to our unit. And our answer also is in pound force foot per pound mass. So it's around 9,800 minus 1,000 times 6.5. It's around 3,300. Let's just look the choices. This is letter B. Okay. I hope there are no questions, but again, if you have questions, just tell me in our comment section or you can connect with me directly. Okay. Next, gas is enclosed in a cylinder with a weighted piston at the top boundary. The gas is heated and expands from 0.04 meter cube to zero point 0.1 meter cube at constant pressure of 200 kilopascal. Find the work done in the system. So actually, we have this one as product of pressure times volume as equal to the work done, right? So we can just say that the work done now is product of pressure times change in volume. So the pressure given is 200 kilopascal. Kilopascal. So that's in kilo Newton per meter square. The change in volume, on the other hand, is from 0.04 to zero point 0.1. So the final volume is 0.1 minus 0.04. The unit here is meter cube. So you can see meter cube will cancel out with meter square, with meter as the equivalent unit. And when you multiply meter to Newton, you'll basically have in terms of joules. So it's already in kilos, so let's just multiply the 200 to 0 0.1 minus 0.0. Okay? That's a 12 kilojoules per kilogram. So from the choices, there you go, you have letters. And next. Okay. So that's the problem, previous problem. Then you have here a 2 kilogram block of metal with a specific heat of 100 joules per kilogram per Kelvin falls from rest through a distance of 100 meters to the Earth's surface. If half of the potential energy lost by the fallen object is converted into internal energy of the block, the temperature change of the block is most nearly equal to 1. Okay, there's a 2 kilogram block of metal, and it was dropped 100 meters to the Earth's surface. It also have a specific heat given, but basically, when you drop a block of metal from 100-meter surface, the block of metal will absorb heat. I mean, so the temperature will increase. And that's the question. How much is the temperature change of the block? But the condition here is half of the potential energy lost by the fallen block is converted to internal energy of the block. Okay? So basically, we solve first the potential energy of the block. So since it came from 100-meter height, the potential energy is mgh. This is now equal to a mass of 2 kilograms. Specific, or the g, or gravity, is 9.81 meter per second square. And then the height of 100 meters. Okay. The value for the potential energy now is has a unit of kilogram meter square meter, or when you simplify that, that's in joules. 2 times 9.81 times 100. It's around 1,962. So it was mentioned in the problem that half of the potential energy was converted to internal energy of the system, which is basically equal to your mc delta T. Why? Why we consider mc delta T? Because there's a change in temperature, and as I've mentioned before, when you have a change in temperature, you always have your sensible heat. Okay? So your change in temperature now is half of the potential energy over mass times specific heat. Okay? We basically have the potential energy as your 1962, so half of that, 1962. The unit of this one is joules. And mass is again given of 2 kilogram. The block of metal was not reduced in terms of mass, so it's still in 2 kilograms. But the specific heat is, okay, this is joules per kilogram per Kelvin, so that's basically good. What's the value again? 100 joules. 100 joules per kilogram per Kelvin. Okay. So as you can see, joules will cancel, the kilogram will cancel. The change in temperature now is in terms of degree Kelvin. Okay. So let me just use my calculator to solve this one. Uh-huh. 2 times, or this is a half, or I can just write it down. 0.5 times 1962 over 2, and there's 100 there, times 1000 over I mean over 100. So, okay, it's around 4.9 Kelvin. From the choices, the closest that we get is around 5 degree Kelvin. So the block of metal now has an increase of 5 degree Kelvin. So if it's around 20 degrees Celsius, or yeah, 20 degrees Celsius, it was changed now to 25 degrees Celsius. Not much of the increase in temperature, but if you increase more the height, that's basically the reason why um, when a fallen debris from outer atmosphere, it has a longer altitude. It is now heated, or the increase in temperature is much higher than what we saw. Okay. So if you get what I mean. And I think that's it. All right. That's my last slide. So let me just end by saying, um, James chapter 1 verse 12, happy are those who remain faithful under trials, because when they succeed in passing such a test, they will receive as their reward the life which God has promised to those who love Him. So take note of this one. This is a very good verse. And we'll see you again next time. I'll be recording more of the videos and for the lecture of different topics in general engineering and applied sciences. So thank you very much again. Sir Deems here, and we'll see you again next time. God bless you all. Bye, guys.